This lecture covers viscosity or low Deborah number measurements for polymeric materials for polymer rheology and processing. Up to this point, we've considered fluids that have flow units or molecules made up of only a few atoms. And there are different considerations when we're talking about flow units or larger molecules with a larger number of atoms. These could be particles or these could be soluble species. But very commonly when we're talking about macromolecular fluids, we're talking about things that are large and are found in food, agrochemicals, pharmaceuticals, paints and inks, and of course other things like polymers in the melt. The challenges that we face with macromolecular fluids that we don't face with, say, smaller flow units are things like heterogeneity and the fact that the flow is dictated by intramolecular forces. So that's something we have to take into consideration. When we are dealing with a polymeric solution, we have to be dealing with dilute polymer solutions to be dealing with something that has a low Deborah number. And the definition of dilute, when we're talking about macromolecules, is a macromolecular solution in which the molecules diffuse independently from one another, and they collide and separate in a random fashion. More or less that they don't actually see other macromolecules very closely at all. And the concentration dependence of viscosity is similar to that of dilute dispersions. We can describe that relationship by this equation shown here, where eta is the viscosity, eta sub 0 is the viscosity of the medium in which the polymer is dispersed, in other words, the solvent or something like that. This symbol is the volume fraction, eta in brackets is the intrinsic viscosity, K sub h is the Huggins coefficient, and 0 is the shear rate. All of which of these are very important when we're talking about relating viscosity of a dilute polymer solution. The Huggins coefficient, which is K sub h, is indicative of the strength of pairwise interaction of polymer molecules, and it can be represented this way. So here we have K sub h, and this is intrinsic viscosity. In this case, K prime sub h, if that's 1, the interactions themselves are just hydrodynamic. That means there are no interactions from van der Waals forces or electrostatic forces at all. If you have attractive interactions, such as those found in self-associating polymers, that results in much, much higher values of K prime H. When we are dealing with a dilute polymer solution, the challenge we face is that a polymer molecule is not a hard sphere, like, say, discrete particles. They occupy a volume that is a function of both molecular weight and interaction with the solvent. And this is a function of hydrodynamic size. And this hydrodynamic size is related to the molar mass of the macromolecule, the chemical structure of the repeat unit, and the interaction between the solvent and the repeat units. So this is different than a hard sphere. Flory-Huggins theory has described this in the past. We talked about the theta condition, but just to review, a temperature-solvent condition that yields an ideal polymer configuration coil in solution is known as the theta condition. And the theta condition yields R sub g, or radius of gyration. Theta condition also defines C star, which is the concentration below which a solution is considered dilute. And if we're below that C star, we can define viscosity this way. So viscosity equals viscosity of the medium with intrinsic viscosity and the Huggins parameter, with C being concentration. We can use the Mark-Houwink equation to relate intrinsic viscosity to K m to the V. K and V are both constants that are obtained from the literature for a given polymer solvent temperature combination. In other words, in the theta condition. If you do have a theta solvent, and the random coil configuration minimizes the polymer segment molecule interactions, you can rewrite the Mark-Houwink equation this way. So the intrinsic viscosity at the theta condition is K theta times molecular weight to the 0.5. This is a way you can relate intrinsic viscosity to molecular weight. And you can do this experimentally using a dilatometer or bubble viscometer or viscosity average molecular weight determination. In this, we can relate this to the Flory-Fox parameter. So this is the equation we saw from the previous slide, shown here for the Mark-Houwink equation at the theta condition. K sub theta is related to the size of the polymer coil by this relationship. So here's K sub theta, and this is phi. This is also known as the Flory-Fox Parameter. This is the root mean square dimension, and m is the molecular weight of the molecule that you're looking at. When you substitute that in the equation at the top, it gives you this relationship. So intrinsic viscosity is related to the Flory-Fox parameter divided by molecular weight times the root mean square dimension to the third. In non-theta solvents, you can determine the Flory-Fox parameter experimentally as an indicator of chain expansion. Those are some situations in which you're dealing with random coils of polymers that do not have any sort of special conditions and just have a hydrodynamic volume. There are a variety of other macromolecules that in concentration are considered dilute, but do not act like dilute particles, and polyelectrolytes are one of those examples. In a polyelectrolyte, these contain charged groups along the backbone, so here we have negative charges, that repel one another and move away from that ideal molecular coil. And this is known as the electroviscous effect. This effect produces chain expansion such that you have to detail the chemical environment very specifically when you're talking about polyelectrolytes. In other words, the salts that are present in addition to solvent in concentration. Some common polyelectrolytes are shown here. We have polysodium styrene sulfonate and polyacrylic acid. The chain dimensions that you see in these two polymers are a function of pH of this whole system and of the salt concentration present. And the ion type that's present in that salt is extremely important. If you have a sodium salt, it differs significantly from the way a calcium salt behaves. So we'll go into that next. So here we have polyacrylic acid and water, all stretched out, all those charges repelling one another. When you add sodium chloride, in other words, normal table salt, you neutralize these charges, and it collapses back down into more of a random coil again. So you can create a random coil from a polyelectrolyte in an aqueous solvent by the choice of the right ion in your salt. However, if you want a different effect, essentially an opposite effect, you can use calcium. And what calcium does is it binds strongly to the carboxyl groups that are found in the backbone of polyacrylic acid. So here you have your calcium ions, and here they're complexing between two different polyacrylic acid chains. And you can have a very low polymer concentration, but it creates multi-molecular associations that are like physical cross-links. A lot like we saw when we cross-linked the polyvinyl alcohol with borax. And this can give you a gel structure at very low polymer concentrations. So polymer concentration similar to that of a dilute polymer solution that should have a low Deborah number, but something that acts very, very viscous instead. Because of their interesting properties, polyelectrolytes have applications that are related to modifying flow and stability properties of aqueous solutions and gels. These are often used as thickeners, emulsifiers, conditioners, clarifying agents, and drag reducers. They can be used as flocculants in water treatment and oil recovery. They are often used in personal care products like soaps, shampoos, and cosmetics. They're used in hair gel quite a bit. They're also found in food, and you have these natural polyelectrolytes, pectin, which comes from fruit, carrageenan and alginates, which come from seaweed, and carbomethylcellulose, which is a functionalized cellulose from wood. Polyacrylic acid itself has an unusual property that can absorb many times its own weight in water, and polyacrylic acid is the active ingredient in baby diapers and adult diapers to absorb multiple insults, as the industry calls it. Another situation that polymer scientists will often deal with are surfactant solutions. So first I'm going to describe surfactants to you a little bit. This is the description of surfactants. Surfactants typically have a hydrophilic head, shown here, and a hydrophobic tail. And this hydrophilic head can be a variety of different things. It can be non-ionic. In other words, it typically has no charge, but some kind of hydrophilic atoms like oxygen in it. It can be anionic with a negative charge, cationic with a positive charge, and then you can have a combination of both negative and positive charges for an amphiphilic hydrophilic head. These are used to create micelles, and this is a micelle shown here in an aqueous solution. So you have your hydrophilic head pointing out toward the water, and your hydrophobic tails pointing inside. And this is an aggregate of surfactant molecules dispersed in a liquid colloid. It may not be an aqueous solution, it could be a more hydrophobic solution, but typically you're dealing with aqueous solutions when you're dealing with surfactants. A typical micelle in an aqueous solution forms an aggregate with the hydrophilic head in contact with a solvent or water, sequestering the hydrophobic single tail in the center of the micelle to give you that kind of three-dimensional ball structure. And this leads us to the definition of the critical micelle concentration, or CMC. And this is the concentration at which surfactants above that are added to the solution will form micelles, and all additional surfactants added to the system will go into these micelles. Below the CMC, surfactant concentrations are so low that you really can't differentiate between the viscosity of the solution and that of the solvent. So it's basically like an aqueous water-like type viscosity. But once you have reached the CMC and gone above it, the system becomes a dispersion of micellar clusters. So you start to get a rate of viscosity increase that increases with surfactant concentration. And close to the CMC, micelles are spherical. And then you can relate this equation to determine viscosity. So here we have volume fraction, viscosity of the solvent, and the shear rate gives you the viscosity of the overall system. However, when you increase concentration even more and you go away from the CMC, these micelles can become elongated and form complex viscoelastic phases, and you start to move away from that low Deborah number behavior. And the phase behavior is strongly dependent on components. And one example of this is shown here. You have viscoelastic lamellar sodium dodecaanoate in 25% weight in water. This is sodium dodecaanoate or sodium laurate. And it forms lamellar phases which are viscoelastic. However, when you add something more to this, you would think, well, maybe it'll become more viscous. It doesn't. It actually switches the entire system into a low viscosity microemulsion, which once again acts like a low molecular weight, low Deborah number material. So what happens is this situation changes so that the micelles, the surfactants themselves, can surround this hydrophobic species, and they form into micelles in water with the dodecane in the center. And these hydrophilic heads shown here pointing out toward the water, and this hydrophobic tail pointing in toward the dodecane. And this changes the system from a viscoelastic system back to a viscous system or a low Deborah number liquid system. Basically, overall, when you increase concentration, you start to see non-Newtonian behavior. You move away from a purely viscous system, a purely liquid system, toward viscoelastic systems and non-Newtonian behavior. And such non-Newtonian behavior includes shear thinning and extensional thickening. The higher the molar mass of the polymer, the more marked this behavior becomes. So at this point, we are no longer talking about low Deborah numbers, we are talking about viscoelastic type Deborah numbers and responses. And so this is what we'll start to talk about next in subsequent lectures, is linear viscoelasticity. Thus concludes low Deborah number and viscosity. Thank you.